Hi, I'm Isaac. I'm a research scientist at Heliax working on the Anoma project, and I want to talk about some research on controller tags, which are a scheme for tracking and maintaining integrity across domains. So the link is actually a draft version of the paper. We've actually refined and simplified some of it, which I'm going to talk about here. But the core concepts remain the same if you want to read about it. We'll try and get an updated version up as soon as we can. The setting for our research is, of course, blockchain land. Specifically, we're looking in a multi-chain setting. We have different chains running with different consensuses or what have you, each with their own trust models. For our purposes here, it doesn't matter if they're L1 or L2 or whatever. Just that each one is a unique domain that can fork or even halt under potentially a different adversary model. But the purpose of each instance is to maintain a state machine. Consensus lets you maintain a replicated state machine. You could just run a controller or a chain or whatever you want to call it on a single computer. But for our purposes, the relevant thing here is that each instance is some kind of state machine. It has some state, and it transitions from one state to another using serializable transactions, or at least that's what it's supposed to do when it's behaving correctly. We're going to call each of these a controller. So each chain is a controller, each individual computer can run a controller, and the reason we call them that is that they control the current state of mutable digital objects that live in the state machine. So in this setting, I want to talk about those mutable digital objects. This is any object that has some state, which can transition via operations on that state as part of those transactions. So a bank account is a mutable digital object. A CryptoKitty is a mutable digital object. Pretty much all the objects in object-oriented programming are mutable digital objects. And for our purposes, I'm going to simplify this down to our very minimal model of stateful objects, which we call resources. So each resource has an identity, it has some contents, but its only mutable state is that it is either not yet created, so this resource doesn't exist yet, created, so it has existence in some sense, or consumed. It no longer exists. And the only allowed operations are the transactions that precisely move the object along this life cycle. So they take a resource that is not yet created and create it, or they take a resource that is created and consume it. And transactions do some combination of these for some combination of resources. Part of a resource's content is what we've been calling resource logics. So these are predicates that dictate the conditions under which they can be created or consumed. These predicates can include statements about which other resources are in what other states. So in practice, you can model more complicated objects as collections of resources. For example, you might end up under the hood modeling some object as a sequence of resources where only one at a time can be created, and thus to create a new one, you would have to consume the old one. The currently created resource thus represents the current state of our object. The reason we like modeling state this way is that it's simple, but it also fits really well into how state is modeled in zero-knowledge proof systems. These resources generalize the kinds of UTXOs you get in Zcash and Nemata and similar zero-knowledge proof stateful systems. We have a whole other project formalizing exactly what resources are and what you can do with them, but that's not what I'm here to talk about. Now, every mutable digital object, including resources, needs a controller to dictate what the current state of the resource is. For our purposes, controller states therefore include resources. So transactions modify these resources. Each transaction consumes some set of resources on the controller and creates some other set of resources. So for a given resource, how would I know what the current state is? Well, it has to have some kind of information associated with it, some kind of tag, which tells us which controller state is definitive. So there are two relevant parts here, and they could have different controllers. There's the creating controller, who tells us if this resource has yet been created. And the terminal controller, and I'll go over later why we call it that, who can tell us if this resource has yet been consumed. Most resources have the same terminal and creating controller. So you can think about these same controller resources and the transactions that only deal with them when there's no transfers between controllers. Then we have fully independent controller states. These can operate in parallel, updating transactions governed by each resource's logic without any kind of interaction, and that's great. things operating in parallel are scalable in very excellent ways. Things get tricky when you want to do transfers, when you want to move a digital object from one controller to another. The classic case where this happens in blockchains is where people want to move tokens from one chain to another to do some trades there. So I want to look at a very high level at where you do transfers in like IBC 20, IBC ICS 20, which are at least emblematic of a fairly standard pattern here. And we're going to try and generalize it and see where we get. So with like IBC ICS 20 style transfers, we can imagine consuming a resource on controller A and creating a new wrapped resource which can in turn be consumed on controller B. At some level, the thing which we created on controller A, which can be consumed on controller B, is a resource with a different creating and terminal controller. Resources of this wrapped kind can be created and consumed on controller B according to their own rules. They can be traded around on controller B. We can even wrap a wrapped resource. We can send it to controller C and whatnot. Such resources have wrapping layers. They encode a kind of history of where they've been. In programming language terms, this is essentially taint tracking. It's keeping track of who could have tainted this token, which in this case means who could have messed it up or could have some forked history of some other version of this token, which you might need to check for if you were worried about double consumes. In the simple case, this is just all the controllers this token has ever touched. Where things get really interesting is in unwrapping. Sending a wrapped resource back where it came from and somehow recovering or producing a version of the resource of the original unwrapped type. This, in some sense, removes some information about the history. It removes taint, but it does it in a safe way. So let's look at these layers. Basically, the relevant information here is a fully ordered list of sends, from A to B to C, representing where the resource's ancestors have been. Fundamentally, if any of these controllers were corrupt, then this resource could have an invalid history. Its ancestors may have done a double spend or something like that. So this brings me to the first version of the main invariant we want to maintain, which we call consistent controller tags. If every controller in this list is safe, then the resource has a consistent history. When you use a resource, you are in some sense trusting the controllers in this list. The usual rule of trust applies. You can only be hurt by those you trust. No one outside of this list should have been able to corrupt this resource, should be able to hurt you in that particular way. As an aside, what do I mean by consistent history? Well, by this I mean that the history of the resource is formed by valid transactions, none of which consume the same resource. A corollary would be that these transactions are serializable. There's some serial order of them that you could consider canonical, and if you ran all the transactions in that order, you get the same result as the current state. I'd note that anyone out there playing with CRDTs, unlike general purpose data structures, do not need consistent history, which is the cool thing about them, and it makes them so much easier to keep track of. Okay, so if we want to maintain CCT, then each resource needs a consistent history if every controller in this list is safe. So each of these wrappings represents a kind of tag with information about controllers related to this resource, and they have a list of controllers, a creating controller who actually created this particular resource, and a terminal controller who consumes this resource, or at least has the power to decide when it is consumed. Note that the terminal controller is always the end of this list. That's actually where the name comes from. When we unwrap a resource, we remove the last element of the list. Under this condition, the creating controller might not actually be in the list anymore. This is a peculiar scenario. It requires that the recipient, in this case B, has to review and, in some sense, attest to the history that happened on C. In the simple token case, that the important property that's attesting to is that no more tokens came back than were sent. Then, promising not to attest to any contradictory history, B assesses whatever happened on C, declares that it, in some sense, might as well have happened on B, and removes this history information from the tag. We no longer have to trust C to use this resource. So how do we go about generalizing these pieces? Well, we're going to have explicit tags for each resource. Creating and terminal controllers are pretty much exactly the same. But instead of a list, we're going to have a DAG of controllers. Conceptually, the terminal controller is in effect the sink of this DAG. It determines if this resource has been consumed. Just for these slides, I'm going to make some simplifications on how I draw these tags. I'm going to stop drawing any wrapped layers. I'm just going to draw the DAG from the tag, and if necessary, transfer arrow colors to indicate creating controllers. I'm also going to stop drawing transfers with the consume thing and just leave the old resource transitioning into a consumed state implicit. So in a more complex example, suppose we have some resources on controllers A and C, and we transfer one of them to B, and then another, and then we do some transaction on B that consumes both to create a resource that depends on both. This doesn't exactly happen when you're only doing simple token transfers, but if there's anything compositional, even the parents of a CryptoKitty, then this can happen, and the list of tags won't be enough to express what's going on here. Naturally, we have DAG in the controller tag, which includes the DAGs from each of the dependencies. So the basic rule for creating a resource is that the new resources DAG includes the DAG of its dependencies. If you're going to transfer to another controller, you add a new terminal controller at the end. These basic rules preserve consistent controller tags. Resources will have a consistent history if every controller in the DAG is safe. These rules are basically the general rules for taint tracking in programming language research. But there's actually another property that I'd like to maintain. In some ways, it's an easier one. Causal resource history requires that each resource is the result of a valid transaction, and the inputs to that transaction, so its dependencies, also had causal resource history. So in this example, even if B is Byzantine, causal resource history would require that it didn't just make up the resource. It created it with a valid transaction, and it didn't forget or ignore some of the dependencies. It actually had those dependencies in existence. Notably, causal resource history does not prevent double spends. We'll get to that later. In order to ensure causal resource history, we need to introduce a notion of attestation. And this is going to generalize our counting more tokens coming back than going out in the first place. Before B can consume a resource created on A, it has to know that that resource has causal resource history. We'll do this using a notion of state roots. Some unique commitment, such as a Merkle root, to the state of a controller at a time. We'll assume for the moment that we can prove a resource or a record or whatever has this state in the controller whose state root is this in some compact way. That's basically what Merkle proofs are for. Each controller is going to maintain an attestation map. I think this can probably be encoded as in resources as well, if we really want to, but for now I'm just going to talk about it like it's its own thing. Anyway, this is a map from each controller identifier to some state root that we have attested to. Initially, these start at Genesis. Transactions can then update any element. For example, we could update A from Genesis to state 7, or B from Genesis to state 2. But each update requires some kind of proof that there is some sequence of valid transactions from the previously endorsed state root to the new one. If you attest to contradictory histories or alternate forks from what you previously attested to, then you are by definition an unsafe controller, a Byzantine actor, an untrustworthy person. Yes, we are testing to attestation. No, we don't have to attest to what they attested to. Yes, that is confusing. So, given such a proof, we could update B from state 2 to state 4. I know that these update proofs are in many ways where the most computationally difficult part lies. So you could use as proof all of the inputs that the other controller got, and then checking the proof is rerunning everything that controller did from the last state root you attested to the new one. That would be expensive, but you could do it. You could also use some kind of incrementally verifiable computation, like what people do in ZK rollups. But now your controller has to support some kind of incrementally verifiable computation, which can be limiting and tricky to do properly. You can use optimistic verification, like optimistic rollups do, and you have to wait for timeouts and be certain of some kind of commit, but your proof is now sort of less absolute. Finally, you could use trust. If your controller is trusted, if one controller is trusted to speak for another, then these proofs become either unnecessary or, I guess, trivial, depending on how you look at it. Anyway, the big requirement then is that you can't consume a transferred resource, a resource created on another controller, until you've attested to a state in which that resource was created. That ensures causal resource histories, so each resource is the result of a valid transaction, and its dependencies also had causal resource histories. I've been drawing attestations with these dotted arrows to mean that this state of controller B attests to this other state of controller A. As part of maintaining causal resource history, and used in our generalization of unwrapping later, we're going to add some more state to controllers. First of all, each transfer creates a separate send record. This can be encoded as a resource with specific logics, but I'm going to talk about it like it's its own thing. So starting with this transfer from A to B, we have a send record created on A. Generally speaking, when you send a resource, you consume the old resource, you create a send record along with the transferred resource that can be consumed elsewhere. These send records reference the destination controller. They represent a kind of promise to accept resources back if they depend only on sends from this controller, and if the activity on the other controller is attestable. Before you can consume the transferred resource on the destination controller, then the destination controller has to recognize that the resource has been created. This requires that the receiving controller attest to the state of the sending controller in which the send record exists. In the tags that we use for our resources, the elements of this DAG are not going to be just controller names, they're actually going to be references to specific send records that live on the controllers from their history. They represent when this resource's ancestor was sent from one controller to another. So when we go to send a resource that already has an interesting controller DAG, the send record that we create will reference the send records on which the sent resource directly depends. These are basically the send records in the DAG that aren't already transitively referenced by other sends. Drawing this many reference arrows gets really messy, and my diagrams start to become really cluttered. But essentially, this means that each resource's DAG is just a local copy of the relevant part of the great big DAG of send records in existence, spread across various controllers, plus it's creating in-terminal controllers. Technically speaking, this copy can actually be out of date, and then it can be updated, but that's okay. We'll get to that momentarily. So that's how we'll do transfers. The last thing then is to cover how we do reductions. The problem with all of this taint tracking is that controller tags have these DAGs that just keep growing, requiring ever more trust to use the resulting resources. And if you want the resources to be more trustworthy, more usable, you need to be able to remove unnecessary parts of the DAG. Even if you just want liquidity, resources with different DAGs, but that are otherwise similar, are still different types. You can even have a different monetary value, especially if you don't trust one of the controllers in one of the DAGs. Now, bearing in mind that causal resource history isn't good enough to prevent double spends, we still need consistent controller tags. Each resource has a consistent history free of things like double consumes, even if all the elements of the DAG are safe. Or rather, if all the elements of the DAG are safe. So how do we generalize those unwraps from our wrap tokens? Can we ever remove nodes from a resource's DAG? And it turns out that we can. It involves send records, and it involves attestation. In particular, we're going to try and remove the send record on B from this resource's tag. The first part of generating the relevant proof is to pick a send record you want to be able to remove, and then permanently lock that send record as no longer updatable. This prevents weird things from happening with simultaneous reductions. We can actually reduce sets of sends at once, but I'm just going to do it for one here. Next, the controllers of the dependencies of the send that we're trying to reduce, which is in this case controller A, have to endorse the state of controller B in which the send record is set updatable to false. In parallel, the controller with the send record we're trying to remove, in this case controller B, has to attest to the state of controller C, specifically the state that includes the resource whose tag we're trying to update. Then the controller with the resource that we're updating, controller C, has to recognize that the previous steps have happened. And of course, the way that controllers recognize things on each other is through attestation. So it has to attest to some state in which they've completed those previous steps. And finally, we can consume the old resource and create a new one with an updated tag, one in which we've removed the send record. All of its old parents connect directly to all of its old children. In this case, it becomes just the DAG A to C. Just cleaning up this diagram a bit and alighting some stuff. I should note that there are similar steps to update a send record's dependencies, much like we just updated a controller's tag. Once you've done that, you can then update any relevant resource tags that reference that send record to a newer version of the send record, which might in turn allow them to reduce their DAGs. I'm not going to take the time to go through that example here because it takes a while. So that's our generalized version of reduction via attestation. And these send records and attestations are promises that I'll accept back, or generalizations of our original promise that was something like, I'll accept back the same number of tokens I sent out that you get in ICS 20. There's some other operations that you can do with controllers and tags. You can halt a controller. This is a special state transition where the controller goes into a state that can no longer update in any way, so there's no valid transitions out of that state. Resource tags can then get backup controllers, automatically transfer this resource here in the event that the controller is currently on halts. So a halt transition implicitly creates a whole lot of send records. For what it's worth, it also implicitly sets updatable to false for all those send records and all the ones in the controller. The tricky part here is what happens if your backup controller has already failed. So you can have a list of backup controllers and so on. You can introduce an emergency override condition as part of a controller's definition. This is some possibly separate entity who can only sign off on halt transactions, but can't make general purpose state transitions. This is really useful if you have some trustworthy but slow watcher for some fast but brittle system. Notably, resources that have controllers that differ only in their emergency override condition, so most of the time their updates are decided by the same entity. They trust different EOCs to declare them dead. These are still considered different controllers, but they do have some useful properties, like it becomes trivial to do cross-controller transactions, where the same entity that decides on regular updates decides on updates for both of them. You can also add don't remove this flags to elements of controller DAGs for controllers who, for some reason, should never be removed from a resources DAG. For example, a currency issuer is in some way special. No currency resources, however wrapped, are trustworthy unless the issuer of the currency is trustworthy. So these are the key properties that we have focused on maintaining. But given these properties we've been maintaining, we have causal resource history and consistent controller tags. Can you actually check that a resource has a serial consistent history with no double consumes, as opposed to having to trust that the set of controllers in its tag are legitimate or are safe? And the answer is yes, you can. It requires some prove a state root is after proofs from pretty much everybody in the DAG, but you can do it. If these are available, you will even find any failures if there were any. So what you actually need to do is go and gather the state roots that prove the existence of all the send records from the resources DAG, as well as a state root that proves the resource itself was created. And then for each of these, you get the endorsement map, or rather the attestation map, for each of the corresponding state roots, or at least the part of the attestation map that pertains to the controllers from the resources DAG. And then you need proofs that these state roots form a valid timeline for each controller, consisting of only valid serializable transactions. Naturally, if these proofs or attestation maps aren't available, you can't do this manual check, and you're just left with trust. The interesting thing here is that the expensive work of checking serializable resources isn't necessary if you trust the controllers in a resources DAG. And this is a case where a little trust goes a long way, where measurably having some trust integrated into your system reduces the amount of overhead work you have to do and makes the system more available. It's one of the reasons that it's important to keep DAGs minimal. They make resources cheaper to work with if you have to trust fewer people to work with them. And that's the controller tag project. You can find the draft here. Like I said, there's still some writing and polish to be done. We've refined send records a little bit and simplified some things, and we'll get a new version up as soon as possible. Are there any questions?
Thank you, Isaac. All right, questions, starting with Jeremy.
Thank you for your presentation. Since the start of the talk, I was curious because I noticed that even when you were talking about, let's say, a list before you talked about a DAG, you had A going to B going into C. Something that crossed my mind is, what if C goes to A? Do I have A arrow B, arrow C, arrow A, or can I remove the first A? Because technically I can do a reduction because I have a cycle in there. Or
So the thing you can do, okay. Because each of those nodes refers to a specific instance of a send record, the naive thing to have is A goes to B, goes to C, goes to A. What you can do is fuse some of those send records to some effectively later send record. This is a move that I didn't talk about in the list of things you were allowed to do, in which case you would reduce your graph and you'd add a cycle to it, and it would no longer be a DAG. We've been reasoning about these like they're DAGs because that is what happens in the absence of a move like that. And in some ways it's easier to reason about. But fundamentally, yes, you can introduce a cycle.
okay, that is quite interesting.
Thank you so much for the presentation. So I have a very stupid but practical question. I'm just trying to understand the intentionality between transfers from one controller to another. So for the sake of argument, let's assume we have just two resource machines on Ethereum, and there is a kudo or even an NFT issued on RM1. Now, the resource logic for that NFT is that it can only be created once. It can be basically minted once under specific conditions, and that's it. Possibly it can be burned. Now, my first question is sort of, if we burn it, can we create it on another controller? And what actually, like, who needs to do the state change on the second resource machine? And what is the attestation that it was meant to be? So theoretically, you could create a new resource on the second resource machine that says, I'm now being able to be minted if I have a proof that a certain resource previously has been, consumed on another resource machine, given that I know its address. But how can I, for example, know that that's the owner of that resource? And are we thinking about it in that way?
So I've been phrasing these as resources that are created on one controller and consumed on the other. So this means that in some sense, both controllers have to recognize the possibility of our second resource that can only be created if and when your kudo is burned. What that means is that that resource, I've been thinking of it as, is minted. So it is in the created state when that send record is created on the first controller. The second controller then has to recognize that the first controller has reached that state before it can consume it.
So who's sending the send here? Is it the user or is it the controller itself?
Well, someone has to initiate that transaction that that creates the send record and that burns the first kudo and creates the replacement. And I'm imagining that the user is going to be the one who originates that, because presumably burning the kudo requires the user's permission. It has to be committed by the controller for it to have officially happened. That's what controllers keep track of. But it probably is going to be initiated by somebody who actually knows about that kudo. On a more extreme case, you could actually have shielded send records, in which case the controller may not even know that that's what's happening. And it's really up to the user to make that happen.
So and then it's basically, is the social guarantee that the resource created on the second controller actually corresponds to the previous one? Or is it somehow granted by the controller's framework?
It's up to the resource logic. So presumably your second kudo says that it can only be created if the first our second resource is something that can only be created if you burn the first kudo in the transaction in which it was created. Therefore, its resource logic has to be able to read that the CUDA was burned in the send transaction, and that therefore it can be created now. If we can't encode that in the resource logic, then we have a problem because we're not able to express creating the new resource from the old.
I think that makes sense. Thank you so much.
Thank you for the presentation, Isaac. When resources are transferred, are they consumed and then created on the new controller?
They are consumed and created anew. In particular, in principle, a send could come along with any transaction that consumes a resource and then creates some new ones, as long as their resource logic permits them to be created on a different controller. I've been talking about it as if that's not a thing that resource logics will care about, but there's no particular reason they can't have an opinion in this matter. The simplest case would be with like tokens, where the thing you do when you consume one of them is create a new one that's pretty much exactly the same. But in principle, we could have arbitrary other transactions. I'm trying to find where my diagram had resources being consumed and then new ones being created. And I think it was here.
Can you elaborate a little bit more on the state of each controller? Can you elaborate more on the state of each controller and how it's used, for example?
Right. So we're assuming that these controllers are state machines that update via some sequence of transactions one at a time. These transactions can do a few things that we care about. One is they can consume and create resources according to the rules of the resources themselves. So that's basically according to the Anoma resource machine. Another is that they, in the process of creating resources that are consumed elsewhere, can make send records. So send records are encoded in the state somewhere. Again, we can probably encode these as resources if we want to keep the thing conceptually simple. And finally, they include these attestation maps of what they've attested to on other controllers. Encoding these as resources might be interesting, but it might be possible. Likewise, these can also be updated over the course of transactions given the right set of proofs.
Thanks.
Yes, this
That looks like a question.
Thanks especially for the work you put into the illustrations. I think that made it a lot more digestible, so really appreciate it. There's one part where I got somewhat confused, I think, which was about the proof reduction.
Mhm.
And if I got you right there, when you do the proof reduction, you consume that resource and create a new one. In that case, you did it on C.
Yeah.
Now, my question is, in terms of like fungibility, what distinguishes this from any other resource that may have been created on C, like that still links it back to being something that originates from A? Let's say like A is Namada and C is ETH.
Right. So the idea here is that our resource becomes, in terms of just the tag part, the part that says what you have to trust in order to believe in the history of this resource, it becomes indistinguishable from a resource that went directly from A to C, or from a resource whose ancestors came directly from A to C. This makes them fungible. It's one of the reasons it's important to be able to do this, is to reduce resources to interchangeable things rather than having them be permanently stuck in little separate lands. Does that answer your question, or?
Right, so like this thing still, when it creates this new resource, it still has some information in it that's, like A knows it is something that is like validly originally minted on A?
It does. So in this particular instance, we have not removed A from the DAG. So
Okay.
this resource's controller tag still includes A in it.
Okay, got it. So it just it removed everything that related to the history of how it got to C from A.
In particular, we cut B out of the
Right.
DAG.
Okay. So
and
just cut B out.
this
Okay.
was a singular removal example. In principle, you can cut multiple things out simultaneously, but it's annoyingly complicated to draw the arrows, and these diagrams would be even worse.
Got it. Thanks. That answers it.
Any other questions?
I have a question. So you couldn't, for example, the B, because you basically get a cycle, right?
I'm sorry, say again?
I want to understand why you actually remove the B.
So we wanted to remove B in order to simplify this DAG. We wanted to make this resource have the tag A to C. presumably because that makes this resource easier to trust. You no longer have to believe that B didn't double spend in order to trust this resource's history.
And also because that may grow quite a lot now.
Yeah, you're right. These tags can grow without bound if resources just get sent around the DAG a lot, and it's nice to be able to cut down on that.
Cut down the cycles.
So removing stuff along the way is good, but it requires this pattern of attestations.
Right. Okay.
In general, from the
User's perspective, most of this should be able to happen in the background automatically. Although, if insofar as we want to make some of the information involved here private, there may be some complexity there. But
So as much as possible, the hard part, which is these attestations, can be done independent of knowing anything about the actual resources involved if controllers attest to each other's state regularly, which is a good way of keeping track of finding out who is forked, and effectively increasing the integrity of commits. Then you can use those regular attestations to do your controller tag reductions with comparatively little overhead.
one more question.
So you've been using the word trust a lot in the talk, and I've been trying to think what trust is.
Oh
But-
boy, that's a deep question.
So in informal language, trust means I believe that somebody's future behavior will be reliable, or at least that I believe that what I learn about their behavior will be reliable,
Mhm.
right? Is that what's going on here, or is it that we are saying we're picking a particular... well, you know what I'm going to say, right? So, please.
So it is making a statement about what I will learn about their future behavior. In particular, it's making a statement that I don't believe I will learn about the results of any double spends that they did that use both the ancestors of this resource and then they double spent those in some alternative scenario.
But does it mean that, or does it mean that I promise not to accept anything that contradicts what I've attested to?
So attestation means you promise not to accept. Trusting the controllers in a controller tag means you believe you won't see. So when
So-
you look at a resource and you're trying to determine if this is a resource with a trustworthy history, and and I'm telling you you have to trust all the controllers in the controller tag, that is a statement about future behavior that you see. When you're doing an attestation, you are not risking being wrong if you've checked the proofs. You are committing to some history of that controller, and if there are other ones, then you just won't attest to those.
So, just to conclude, I understand that there's two words, there's attestations and there's trust. You led on the word trust, but in the mechanics, all I saw was attestations.
Mm-hmm.
Was that accurate, or have I missed something?
So most of the mechanics revolve around attestations. Where trust comes in is in the use of this consistent controller tags property. It's how do I know that this resource's history is consistent? I know that it's consistent if every controller in the DAG is safe, which essentially means I have to trust them, which is where we came around to a little trust goes a long way at the end. If I trust those controllers, then I know that this resource's history is consistent even without doing the work to check or having some potentially enormous amount of proofs to check.
Thank you.
We need to move on, but thank you all for the lovely questions. Let's give it up one more time for Isaac,